Okay, we're going to talk about what happens if you take the divergence of a curl and the curl of a gradient. So it turns out these expressions are all zero, which is pretty amazing. So let's go back to 2D for a sec. So remember that the curl we called the integrand of Green's theorem. And so it was qx minus py. And if the case was that p was fx and q equals fy, in other words, our vector field was a gradient, then we got fy sub x minus fx sub y, and this is obviously 0. So in other words, the curl is how non-conservative f is, where conservative vector fields are gradients. That's just another terminology thing. So it turns out in 3D it's the same. Same exact interpretation. So the curl is a cross product of our vector field with the gradient. So in the case that f is a gradient itself, look what happens. We get the gradient cross the gradient. Surely this has to be 0, right? Because we know that if the cross product of two vectors has to be 0, because these two vectors are parallel. For example, I cross j, that's k, we should get something orthogonal when we take the cross product. So actually, it turns out the curl again represents how non-conservative. And conversely, if the curl is equal to 0, it turns out this implies f is a gradient. Exactly as we expect. And similarly, because we could think back to the algebraic situation where if we had, let me draw this a little better, if we had that our vector was in fact, or yeah, let me put gradient cross f equal to 0. That's what curl f equals 0 means. So if we know that the cross product of these two things equal to 0, it actually means that v is parallel to a. It's an if and only if thing. So, for example, let's take this just a standard position vector. So in fact, the curl of this thing is 0. Like, for example, we could do the qx minus py. Surely this is just going to be 0 minus 0. And similarly for the others. So, and of course, the position vector is just the gradient of the length. 1/2 x squared plus y squared plus z squared. And that's easy to see. You just differentiate each term. So this particular example, it also shows us what such vector fields represent. So gradient f, these are actually called irrotational. And because if we plot the position vector, for example, in 2D, let's do just x, y, then we see that it's always outward pointing. So there is no rotation of particles with velocity r. Right? Because if we start with a particle and we send it going, it always just goes outwards. It never rotates. So such vector fields are called irrotational in the fluid mechanic literature. So that was kind of a neat trick, right? The cross product of two gradients has to be 0. Well, can we do it again? Because we know that the dot product of a cross product is also 0. Right? Because if we start with A and B, and we end up with a cross product, surely this is a right angle between these things. So the cross product is perpendicular to both A and B. So now let's replace A with the gradient. So what this should mean is that the gradient, and I'm also going to replace B with F, because we like F more than B. So the gradient dot product with the curl should be 0. So in other words, the divergence of the curl is 0. And in this case, we had the curl of the gradient was 0. And this is true, because really it's just the same. You can take the partial derivatives, and you can show that there's a lot of cancellations. Like heuristically, gradient f, we know it's fx, fy, fz. It's all plus signs, whereas the curl, remember, there's a lot of minus signs. So then the curl, with the gradient, there's cancellations. Like fyx minus fxy. And again, the divergence, we remember it's px plus qy plus rz. This is all plus signs. And the curl, again, has minus signs. So surely the divergence of the curl, you'll again have cancellations. Just like fyx minus fxy equals 0. You can go through the calculation, but that's just all there is to it. I don't think it's super critical to go through. I think the important thing is to recognize this dot product relationship and connect it with the usual algebraic situation. Okay, so this also sort of tells us what these things should correspond to. In fact, if we have the converse, so if the divergence of a vector field is 0, it actually implies it's a curl. It's a curl of G. There's actually a G. I can't use little f because little f should be a function, right? So it actually means that there's a curl of some G. So in other words, f is del cross G for some vector field G. And we actually call such things, f is then called solenoidal. It's the counterpart to irrotational. Where does this name come from? The solenoid, it's a thing from physics. A solenoid is kind of like a donut, and it's made out of coils. And if you send a current through the coils, that sort of corresponds to our integral over a closed curve f dot dr. And what you end up getting, the area integral, is that magnetic field inside. I'm not going to explain what I just said, but you'll see it in physics. But the point is that if you have a solenoid and you put a current through it, you get a magnetic field going through this. And in fact, magnetic fields, this thing in here is called a solenoid. That's where the name comes from. And magnetic fields, they actually satisfy 0 divergence. And this is called Ampere's law. And it says there's no accumulations. Remember, that's one of the interpretations of divergence, inflow or outflow. And what this means physically, there does not exist a magnetic monopole. So in other words, you can have a north and a south for a magnet, but there is no such magnet with just north. This does not exist in nature. It has not been found experimentally. So Ampere's law actually tells us, it's the extrapolation of this, and the law is that magnetic fields have to be solenoidal. There's no accumulation of magnetic charge. So if you're wondering what curls look like or what solenoidal vector fields look like, just think of magnetic fields, and that'll give you kind of an idea of what's going on. Okay, thanks for watching.